So as we already talked about in the previous section, a logical argument is made up of premises or assumptions and a conclusion. And together, the premises and conclusion make the argument. Let's try and identify the premises and conclusion of this argument. It says, Joey loves to watch movies. If Joey loves to watch movies, then Carlota loves to jog. Therefore, Carlota loves to jog. The first premise is that Joey loves to watch movies. The second premise is, if Joey loves to watch movies, then Carlota loves to jog. The conclusion is that Carlota loves to jog. So we're assuming premise 1 and premise 2 are true. And then we want to see if the conclusion holds. We could write it like we did in the previous section. Forget these. By the way, in my math lab, there might be problems where you have these 3 dots. In a previous edition of the textbook, there were 3 dots to represent the word therefore, but then they took them out in the newer version. So if you see those 3 dots in my math lab, that just left over from a previous version. It's kind of redundant because the line across also means therefore, and then the 3 dots means therefore, so it really didn't need both. So that's why they took it out, but it just didn't make it out of all of the my math lab questions. Everyone's still doing okay? All right, so how can we analyze this? Well, as I just said, an argument's valid if the fact that all the premises are true forces the conclusion to be true, and an argument is not valid, it's invalid otherwise, and then it's called a fallacy. We're going to analyze this argument with a truth table. Now, Euler diagrams work well with simple arguments, but they don't work well with more complex ones, especially ones with if-then. Can be challenging. And so if the words all, some, or no are not present, it's actually better to use a truth table. If you have the words all, some, or none, or no, universal or existential quantifiers, then you want to use an Euler diagram. All right, so how to test the validity of an argument with a truth table. What you're going to do is assign a letter to represent each component statement. So you're going to change your statements to symbolic form. And you're going to express each statement symbolically. And then you're going to join together all of the premises with the word and, right? Because what we're doing is we're assuming this happens, and this happens, and this happens. And then you're going to say, if all of that happens, then the conclusion is true. So it's actually a big, giant if-then statement. Then you're going to create a truth table for the big, giant if-then statement. And if it's a tautology, if it's always true, then you know it was a valid argument. And otherwise, it's invalid. So let's go ahead and... if you didn't follow that, I'll come back and go over those steps again once you've seen an example of it. If the door is open, then I must close it. The door is open, therefore I must close it. This is the argument that we're going to check if it's valid or invalid. All right, so the first thing we're going to do is assign a letter to represent each component. So P could represent the door is open, and Q could represent I must close it. Those are the only components in here. Right here we have door is open, I must close it, I must close it. Then we're going to actually write the argument in symbols. So we have if the door is open, if P, then I must close it, then Q. That's P arrow Q. And then we have the statement, the second premise, the door is open. Well, that was just statement component P. And then we have the statement, the conclusion, I must close it, which was just Q. So if we want to determine if this is a valid argument, then it would have to be the case that if the first premise is true, and, there's the connective and, the second premise is true, then this whole thing would imply the conclusion Q. So you join together the premises with ands, and then make a giant if-then statement where the consequent, the then part, is the conclusion Q. Now what we want is for this giant if-then statement that we've constructed to be a tautology. So we're going to test that out in a truth table. Okay, so jot down this giant statement if you're taking notes, and then we're going to make a truth table for it. How many components are in this statement? Only two, P and Q. So that means it's going to be a truth table with how many rows? 4 rows, right? It's always the same. When you have two components, you have half true and half false, 2 and 2 for the P, and then for Q you have true, false, true, false. All right, then we need to decide on our column headings. And remember, just like in algebra, whatever's in the innermost parentheses is going to be analyzed first. Unless there are any negations of individual components, we would do those first, but we don't have any here. So going to the innermost parentheses first, our first column heading is going to be P implies Q. All right, then working outward, inside the brackets, we have P implies Q and P. And then we're going to have only one connective left. This is the conditional, so that's the whole statement. P implies Q and P implies Q. I'm going to go ahead and number these columns so we can talk about it. We have column 1, column 2, column 3, column 4, and column 5. We're going to analyze P implies Q, which is column 3 first. And we're going to have to use columns 1 and 2 to do this. We're also going to have to use the rule for the conditional. Remember, P implies Q is only false if you have the promises made and then broken. True implies false. So in this case, where does P show up as true while Q shows up as false? Looking at the first two columns, we see that that only happens in the second row. So that's the only place where this column's going to have a false, and then the rest are going to be trues. All right, now in the next column, we are analyzing P implies Q and P. What's the new symbol here? Well, only this and symbol is new. We've already analyzed P implies Q, and we've already analyzed P. So that means that we are going to be using which two columns? Type into the chat which two columns, 1, 2, or 3, are we going to be using in order to analyze this and statement. Very good. So we're going to use 3 and 1. 3 and 1. Okay, so looking at 3 and 1 and using the and rule. What did the and rule say again? The and rule, P and Q, is only true if both are true. So we're going to look through column 1 and column 3, and we're going to see where we have two trues. Where do we have two trues? Let's see, we have here in the first row, nowhere else do we have two trues in columns 1 and 3. So that's the only place we're going to have a true, and then everything else is going to be false. Okay, now let's look at column 5. For column 5, we have one new symbol again. Each column always only has one new symbol. The symbol we have not yet analyzed is this conditional, right? We've already analyzed everything else. The rule for the conditional, once again, up here is only false if we have true implies false. The promise is made and then broken. Okay, which columns are we going to use to analyze this whole statement here, this conditional? 1, 2, 3, or 4. We need 2 of them. Good, we're going to use 4 and 2. 4 has everything that's in the big brackets. This is going to be 4, and then Q is in column 2. Okay, So we look at columns 4 and 2. Now, since it's the conditional, the order matters. We're going from column 4 toward column 2. Right? The antecedent is in column 4 and the consequent is in column 2. So let's see, like here, we are going from here to here, here to here, here to here, here to here. Now the rule is it's only false if we have true implies false. The only place we have a true in the antecedent is in row 1, but it's pointing towards a true. So that was our only possible false statement, and it's not false. So all of these are true. Okay? So what do we call it when all of the scenarios give us a true? We call it a tautology. And when you're analyzing an argument and you get a tautology for the truth table you constructed, you can conclude this is a valid argument.